All right. So let's get started. I've got a few announcements for you today. First one is that homework 1 is due today. So hopefully you've submitted it to Canvas or sent me something or will give me a hard copy as you leave today. Yep.
Homework 2, you haven't given us that yet? Or was that?
Homework 2 is the packet. Yes, homework 2 is the chapter 2 packet. So the idea is you do it a little bit in class and then you do it more outside of class. That's also not correct. It's not due next Tuesday, it's due next Thursday. The date on Canvas should be correct. There's a homework 3, which in case you want a hard copy, I still have some. I'm thinking maybe give you another additional week to complete homework 3. So that puts us at March 6th. That's the plan for now. Yeah. Any questions on that? Due dates or anything? Okay. I do just want to make you aware there's an award. There is an award that why does it zoom in on everything? Maybe you could not zoom in. There's an institute on campus that, in honor of Brother Camillus, gives out a grant. So if that's something that you're interested in, you can use it for something like Janterm or study abroad. I realize I'm talking to mostly seniors, so that may not make sense. But if you have a research trip that maybe you're thinking about, or supplies or anything, feel free to apply. That's due at the beginning of March. Okay, so my plan for today is we're going to work on chapter 2. We're hopefully going to finish chapter 2. We may or may not start data structures. In case we do start data structures, the plan is I'm going to talk about what the unit's going to look like. We'll go over some different structures at a high level. And then this next unit's going to be one for the videos that I talked about on the very first day. So I'll talk about that. I'll put you in groups. And then the plan for that is, since we go over most of the slides at the beginning, the rest of the time for that unit is mostly just spent doing problems. I've got another packet. And then, so we'll do half class time of those and then half class time of you're working in your groups. And it's extra office hours for you to discuss and work on things. But I'm getting ahead of myself. That's where we're going. But for today, I want to, before we continue with the slide deck, I just want us to practice a little bit more with the sort of equation things we talked about last time. So let me zoom back through all the slides and remind you where we're at. So we're talking about big O, big omega, big theta, right? These asymptotics that help us define how to bound a function that we're given. The idea is we have an upper bound and we have a lower bound. And then if those two are the same function, then we've got an average case bound that helps us to really hem this function in. So the idea for the upper bound is we choose some function g of n, and then we pick two numbers, one of which is c, a constant, which gets multiplied by that function that we chose. And the other item is n naught, n0, which is the value for which after this point, the function is going to be bigger than the function that we're given, f of n. So we choose a function, g of n, we pick two numbers, c and n naught, and once we do that, then we just show that this is as it's going to happen as expected, and then we've got our big O. Lower bound is very similar process. We're just looking at when the value of c times g of n is less than the function we're given. And then the average case bound is if we found the same function for both the upper and lower bound, then we can say that function is big theta. Okay, so we spent some time on 3n squared minus 100n plus 6, where we got to a point where we saw that n squared is our g of n, where our c was 3, and our n is, I believe it was 1. It's hard to see when I'm staring at this. I think it was 1. For our n naught is 1. And so once we have those, we say that the big O of f of n is n squared. We did that for big omega, where we saw that c is 1, n naught, we said it was 50. And so once we do that, then we say that the big omega of f of n is n squared, and we write it something like this. And so once we have those two things, then we can just say the big theta of f of n is also n squared. We looked at this again with function 2 to the 2n plus 1. And so now I want to solicit equations from the audience, and then I'm going to, I've got my markers, and I would like you to go up on the board and try and figure it out. Since I'm getting the equations from you, I don't necessarily know the answers beforehand. Chances are I could figure it out pretty quick, but the goal is also for you to figure it out pretty quick. So would someone like to share their favorite equation? Hopefully in terms of n. Go for it.
Never mind, I'll try out.
Okay. In terms of n. Any ideas? Yeah.
4.
4n cubed plus 2. Anyone else? Hoping for maybe 4 or 5 of them. Come on, just make something up.
4 to the 4th plus 2.
Cool.
1 plus n.
Well, wait, I missed the second half of that.
So like 6 by 5. Perhaps like trying to do like algebra and have to use like equation to this. I'm sorry, I'm really trying to explain this. I'm really trying to do it.
What's the equation?
1
1 plus n plus 2? 1 plus n equals 2. I think I would just stick with 1 plus n. Yeah. Ooh. Oh. Okay. Someone give me exponential with n in the exponent. No, n in the exponent. Yeah. 2? Where's the plus 5? Is it in the exponent or below? Okay. Other ideas? Do you e to the n? Maybe one more? Yeah. 5n. Okay, so I'm gonna go distribute markers, and you guys pick one of these, or
We're finding upper lower.
yeah, so it's big O, big omega, and big theta. Sorry, I'm thinking how I want to do this. I'm gonna say, okay, this area, define a group. You get both I'm gonna give you all three of these. This area, all three of those. That corner, define yourself, you get n cubed factorial. You two in the back, you get 2 to the n plus 5. The middle back corner, you get e to the n, and then the front area gets log base 2 of 5n.
I'm sorry. You didn't add one. How do you even feel? It's 5 in, that's a big X. I would think that you're probably maybe right. One thing is, that's kind of like that's a following the effort here is I think that makes sense. Yeah. Oh, yeah. Plus, I know what and I do know or the max
I'm not convinced that the big O of e to the n is n. Oh, your g of n is e to the n. Okay. Yeah, so make sure to write it as like e to the n equals, where this is your f of n is equal to O of e to the n. Because the way that I read it, it says that the big O of e to the n is n. Okay, so then we have n plus 5.
Oh, like the.
Okay, so I think it's fairly clear to say that the big O of this is n cubed. And I think we could argue that big theta is n cubed for this one. N to the fourth as well. Like, I feel like that's fairly straightforward. This one would just be n. I'm not sure that I mean, I think I buy it that like our constant can be 2 to get, wait, hold on. Let's open Desmos. N cubed factorial. And that just looks incredibly wonky. Do we think we could reduce this in any way? Or is it just always gonna be n cubed factorial? Yeah, I mean, it's factorial, so we're kind of stuck with that. Okay, so we get theta of just the same function. For this one, 2n to the n plus 5, it's just 2 to the n. I hope you can see like a pattern kind of going here. Yeah. I think that's the goal. Like because for big theta, yeah, so something is in big theta if it's both an upper bound and a lower bound. And like we can manipulate the upper bound in a way so that it's above and the lower bound so that it's below. And so something is in big theta if we can say it can be both an upper bound and a lower bound. That may not be true for all kinds of functions. But for these ones, the easiest way to find a g of n is to like simplify the biggest term that you're given and just ignore the rest. And remember, like these are sets, right? So there's infinitely many functions that could be greater than, like we could have chosen probably like n to the fourth factorial. And that's still valid, but maybe we just want to approximate it with n cubed factorial. Okay, for e to the n, this is fairly straightforward as just e to the n. Anybody do log? Yeah.
We didn't write it down on the board, but we think it was just log 2 of that.
That makes sense to me. Think you could argue that. Right, because we like ignore the constants. Okay, and then these are just notes. Sounds good? Seems a little bit more manageable, I hope. Okay. So let's continue. So we talked about the growth rates and dominance relations. We saw this big fancy table that shows us here's how these different classes of functions grow. And so we saw that log n and n seem to do the best. Log n is preferred because even when we get up to this billion, 100,000 million billion, when we get up to like 1 billion data points, then this is still really fast. This is fairly fast. This is passable. This is not. So when you design algorithms, it's really important to think how, like, what's the complexity of this? Because if you design an algorithm for something that could get really, really, really big, then if it's like an n squared or worse algorithm, then you're going to be out of luck. Talked about that. So now it's the classes of functions, which is basically just me telling you and showing you here's kind of what the graph looks like, which you can also do in Desmos, where we've got constant functions, which is just like a straight line, happens instantaneously, the best kind of function because it takes no time at all. Logarithmic functions, which are sublinear, which just looks like log n. Remember, so let me skip ahead through all of these slides and remind you what exactly a logarithm is, where when we say log base something of x, the base is the base of the number, and then this is an attempt to get at like the exponent y. But we've got x on the other side. Typically, we use logs when we're dividing repeatedly. So like binary search is log of n because we keep dividing the array in half as we look for something. So in that case, binary search is log base 2. So when you're looking for a log algorithm, think dividing. Okay, now I'm going to skip back to where we were. Linear functions are just in terms of n, fairly straightforward. Superlinear are when we are doing maybe some dividing, which is where we get the log n part, but we do that n times. So that's where we get quicksort and merge sort, because even in there we're dividing it to some extent, but we're also doing that n times. So we have to, that makes it superlinear, where we have n times something. We've also got quadratic functions. I'll move this thing up. Which is n squared, which is like the parabola. Cubic functions, n cubed, which since we don't really care about below 0 at all, we're just looking at the I forget the numbers of quadrants. It's been a while. I think is the positive the first quadrant? Okay. Yeah, so we're looking at the first quadrant here, in both quadratic and cubic. And cubic just grows a little bit faster than n squared. We'll look at dynamic programming algorithms in this class after we're doing data structures, and then I think sorting, and then dynamic programming. So we'll look at some of those algorithms. There's also exponential functions, like with a constant to the power of n, which, for example, enumerating all subsets is 2 to the n. And then we've got factorial, which is like if we want to generate all permutations or orderings of something. I honestly don't know why it goes like up, down, up, down, up, down, given that factorial generally is not defined for n less than 0. Typically, we have 0 factorial equals 1 factorial equals 1, and n less than 0, like, who knows? So again, we're looking at that first quadrant in the graph. But this, like the slope here is even bigger than the exponential. And remember that factorial like really doesn't make sense unless your data set is super, super small. Okay, so this is the other packet problem, which is basically just writing this down. Where these like double greater thans means this, the thing on the left. So if this is, the thing on the left is A and the thing on the right is B, A grows faster than B. Because we can read it left to right, like A is greater than B. And so the thing on the left grows faster than the thing on the right. So like n factorial grows faster than log n. Anybody need more time to write this down? I see writing. I'll pause for a second. Okay. Moving on. This, it gets into the part where I mostly just want to skim over this because some people haven't had calculus. And so just to make you aware. The idea for adding, if you ever need to add like the big O of two things, this is really confusing. So let's say we have f of n and we have g of n, and those are both approximated by a big O of n squared. If we decided to add these two functions, we get to O of n squared as well. But there's some things that we need to be careful of in doing that. If you would like more information about this, I will refer you to the textbook. Multiplying, if you have a asymptotic of some function and you multiply it by a constant, we can ignore that. We've seen this before where it doesn't change. And then if for some reason you want to multiply like big theta of f of n and big theta of g of n, you just need to make sure to multiply those two functions together. And that's why nested loops take O of n squared, because the inner loop takes n and the outer loop takes n, and you multiply them together. Okay, so I just want to address the summation formula that you might see in places. This is, it's structured like, we can read it kind of like a for loop, where it's got this crazy Greek letter, but once you understand the parts, we can figure it out. So this is equivalent. I don't actually know that I like this. I don't like that they're all n. Sorry. I'm going to change this. Let's call this I, call this I, and we leave n. So this is equivalent to saying, for I in range n in Python, and then we say, like maybe we have a sum equals 0 up top. We say sum plus equals I, and that's it. Like the big sigma is just setting up saying, hey, we're going to sum a bunch of things together. And the thing on the bottom tells us where do we start. Also, what is the thing that we're summing called? In this case, it's I. The top tells us here's where we start. So that's this bit in the for loop of where do we stop. And then the thing right after it is what are we summing? So sometimes it's just like this, just I. Sometimes it's something more complicated than that. But the idea is we're always doing sum plus equals whatever is in here. That's the idea. You'll sometimes see like a big pie as well. That just means multiplying instead of adding. So instead of plus equals, you would probably have like product equals whatever, and then product times equals whatever is right here. So that's just what that notation means. That way you can read it when it shows up. We addressed exponents at least twice before, just to remind you how those work. And then we also briefly discussed logarithms. I would like to keep my annotations. Okay. It's 2:15. We have until 3:10. And we have problems. Problem 6, 7, and 8. I'll let you take a stab at. Let's say maybe I'll check in at 2:30 and see how we're doing and make a decision then of where to go next. So work in your groups, work on the packet problems. And also work on the homework if you guys finish that. And I'll check in 15 minutes. All right, let's go over it. Is the big O of 2n plus 1 equals to 2n? Like, yes? What's my solution? Can I get a thumbs up or a thumbs down if this is yes or no? Thumbs up, yay. Also because we did this already. I need to change that for next time. What about the other one? Is the big O of 2 to the 2n equal to O of 2n? The answer is thumbs down. The reason why, let's see, do I have space in the PowerPoint? Not immediately. Wait, no, I need to do this. Let's show. Remember exponents, so 2 to the 2n is equal to 2 to the n plus n, which is 2 to the n times 2 to the n, which before we had just 2 times 2 to the n, but since the n's in the exponent, we can't just discard it willy-nilly, so it's not the same. So writing this out and saying no, that's fine. Like that's enough work. To just say that answers the question. Yeah, there was a question of will this be on the midterm? The answer is most likely yes. I have not written the midterm, but you can bet on there being some of these questions. And that's kind of what the packet is here for, to like give you practice for exam problems. Okay, anybody need more time on this? Okay, I'm about to switch to another document. 3. I'm also going to post the updated version of this on Canvas. Yeah, question. Problem 8. Yeah. I don't think it really matters. You can make an assumption. Typically, I think assume either 2 or 10. I don't, yeah. We typically just ignore the base and just say log. If the base really matters, then you say it. Otherwise, it's just log. I think it's usually assumed to be 2, though. Okay. We skipped a problem in there. Where's problem 7? There's problem 7. Someone want to share what their so we have G of n, but what's your C and N naught for, let's say, big O? Yeah.
At 0.1.
Big O for 0.1 and 1?
Yeah.
I think that may be big omega.
Or yeah, sorry, yeah.
Yeah. So big O
Oh,
upper bound.
2 and
2 and 1? Okay. Anybody else have something different?
1.
1 and 1? That works? Yeah. Anybody else? Yeah.
Big O at the C one. And 9.
Yeah, I think n, we would want it to be discrete values. So for n naught, make sure it's just a whole number. So either, I think in this case, 1 is acceptable, so you could round down. Otherwise, just round up. What do you get for omega? I mean, you shared it was 0.1 and 1. Anybody else get something for omega? I mean, that works. The thing, like, this is the thing that I'm gonna keep reminding you. There's infinitely many possibilities that you can choose, right? Like if C equals 1 for the big O, then then you just choose like a number between 0 and 1 for big omega, and there's infinitely many numbers between 0 and 1, so pick one of them. Similarly, there's infinitely many values of n naught that you could choose, so just pick one of them. And if you can graph it and show it, then that's fine. Yeah.
Big O is the other part, right?
Yes. Big O upper bound. Big omega lower bound. 2 of them together, theta. Okay. What'd we say for problem 8? The first one, thumbs up, thumb down, true or false? See some thumbs up. Thumbs up. That's true. I mean, I think hopefully by now we can kind of see intuitively that the big O is n squared. You can prove it if you want to. Okay, for 2 and 3, these two are mutually exclusive. So show of hands, who had 2, the second one, to be true? Hopefully nobody. Who had this third one to be true? Hopefully everybody. Okay, so let's talk about it. What are our functions? Square root of n and log of n. Square root of n and y equals log n. Okay, so just immediately, just by plotting these, we can see that square root of n, the red one on top, grows faster. They look kind of similar, but square root of n grows faster than log n. It is possible to like manipulate square root of n to where it looks like it goes under. But the reason the first one isn't true is just if we look at the functions by themselves, we can see that square root of n grows faster than log n. So that's why the first one is not true. But the other way around, because log n it grows slower, then we can say the big O of this can be square root of n. That's probably not the best upper bound for it, but it is an upper bound. Remember, infinitely many possible functions. All right, what about the last one? True or false? I see false, false, false. Why not? Yeah. Right, yeah. So let's see, we've got, yeah, there's just an n squared in front of it. N squared. Yeah, and since we know that square root of n is bigger, it grows faster than log n, then that gives us our answer. Awesome. So I think I'll have you turn in these packets when you leave. If you're not here in person, then you can turn it in on Canvas or give it to me later. That's also fine. Probably won't give it back to you for a couple days because I have to grade other stuff. Yeah, I will. Yeah, so turn in the chapter 2 packets at the end of class because we're done with them now. Question. Question on problem 2. For the expert whiteboard. Yeah, let me talk. I went around the room and talked about it, but let's talk about it in front of the microphone. So for the x squared plus y squared, there was some confusion and also maybe my mistake. There's 2 options here. One of which is if you consider x squared, x and y to just be constants. That's the easy way where you can just say that this function is O of 1. The harder way is to consider that instead, maybe I should have typed f of x comma y. And then you find what's the big O of that. And so that's just a matter of finding constants and n naughts like usual. Yeah. I think the book says the big O is x squared plus y squared.
Yeah.
Constant, yeah. Mm-hmm. Big O of wait, let me draw. What are you thinking the big O might be? N squared? For the case where they're constants, probably. Because like if you've got a constant function, then like n or n squared would be bigger. So yeah, technically.
That's not. That's not.
Correct. Yeah. Any other questions?
So the math background, that's.
Math background question is homework 2.
Oh, okay, that's okay.
All other packets are just Yeah. So just the math background packet. So you're hanging on to the math one until, yeah, online or hand it to me or drop it off in the box outside my office. Any of them work. Okay. All right, so let's start data structures. Are we good to go? Nope, that's not what I wanted to do. Maybe it helps if I close the other version. Nope, not settings. Where did it go? Open recent. Data structures. Okay, there we go. All right, so we will start data structures now. And I will begin by telling you what this is going to kind of look like. So we're going to go through the structures in general. And then once we've kind of learned, here's what these are about, the goal is for it to be like a cursory overview to show you, here's how these structures work. And then your goal is to go more in depth as you work on the videos. So the groups for the videos will be random, at least for this assignment. I will hear arguments for future videos if you would like to choose your groups. But for the first video, it's going to be random just to get you to talk with other people that are sitting elsewhere in the classroom. In terms of the topics, I believe we're gonna go over like a bunch of them, but I'm only gonna give you a choice of 3+ data structures, which are binary search trees, priority queues, and hashing / dictionaries. Just because some of the other ones that we'll talk about, you've all seen before and form more of like a basis. So we're going to go over the structures in general. I have a bunch of pictures that I've picked out from the internet to try and show you this is how these data structures work. I'll tell you, here's what the main operations are, and here's what the complexity of those operations are. Your videos are going to go into more detail and actually prove it and show me that this operation is what we say it is. In terms of the packet, we'll do these slides, and then the next few times we'll come in class, we'll just work on the packet for part of it, solve problems, and then the other part of class is get with your group and meet, and then I'm also available if you've got questions. Any questions, concerns with that so far? Okay, I haven't given you a ton of detail yet. Trying to decide. We've got 20 minutes. Trying to decide whether I want to show you the video assignment or just start with the data structures. Maybe I'll show you the video assignment first, so that way you know kind of what is important to retain as we go through the data structures. I will mention that these are the data structures that we talk about. So contiguous or linked, so linked lists as well. Stacks and queues, dictionaries, we'll all kind of talk through. I'm not a fan of how the book presents dictionaries. I feel like it's a little unclear. And so I would like to combine dictionaries and hashing. Or you can combine them if that's what you're assigned, if you so choose. And then binary search trees, which hopefully you may have a little experience with. Priority queues, which you may or may not have worked with before, and then hashing. So that's kind of the data structures that we'll talk about. Later on, I think in sorting, the book talks about heaps. So we'll all talk about that together. Yeah. Okay, where's that? It's over here. So let's just spend the time talking about what the video looks like. So you're going to be assigned to a group, and I'm going to assign you a data structure. And your job is in your group, you're going to script, film, and edit a 5-minute video, 5 minutes or less, to explain the data structure. You can break it down into roles. That's what I've done in this assignment. I've said this is like the different roles that you need to look at. Your group, once you get together, you may choose to structure it differently. But I've provided a structure for you, take it or leave it. In terms of what you turn in, it's going to be a YouTube link. So upload it to YouTube. And that way you're not sending me like all these huge video files. So upload it to YouTube and then also send me the code that you write. So there's, oops, I forgot to type that. I'll update this. So in terms of the code that you submit, I'll talk about this with the programmer. You're allowed to use code that you find on the internet. You're allowed to try and use AI to write code for you. But you have to understand what's going on. And so you have two options for submitting code. One is publish it to GitHub, and the other is turn in a zip file to Canvas. If you use code majority from other sources, stuff that you didn't come up with yourself, then you have to turn in a zip file and you can't publish it to GitHub like you wrote it all. That's my rule. If you do write it mostly yourself and you publish it to GitHub, I'll give you 5 points extra credit. So that's my incentive. And either one of these, it should be independently executable. And so you should include a README telling me, here's what language you need, here's what packages you need, here are the commands to run it. So 2 things you'll turn in, YouTube link, code. Okay, so here are the roles that I've come up with. One of them is the architect, which the objective is to illustrate and demonstrate the data structure in action. So your job is to come up with 2 toy examples. Toy examples meaning like dummy data, something that's just for demonstration, easy examples. So 2 distinct examples and draw pictures and show how it works. And the architect's also responsible for figuring out proving the efficiency. So I'll give you the numbers in class and you prove that that's the case for those algorithms. Okay, that's the architect. The architect's job is to be able to explain it. Like here's the example. That's the teacher kind of role. The programmer, sorry, I was editing this up to like the lunch hour, so some of it is missing. I'll fill it in and re-upload it to Canvas. Your main objective is to implement the data structure. So the programmer should come up with some non-trivial example. So like the toy examples, those are trivial, probably small. come up with a bigger example. So search for a real world data set or use a random number generator to generate something. Implement the data structure from scratch in a programming language. I don't care which one, choose your favorite. And then use that non-trivial example to demonstrate here's how it works. I have some caveats here. So none of you are going to be assigned linked list to implement. So that's my example. If you were assigned a linked list, you shouldn't use like Java's linked list API. Because the goal is to rewrite those structures in your own code. And then that's my caveat for you don't have to start from scratch. You can use code that's elsewhere on the internet. And the thing that's required of you is that if you do so, you must cite your sources, both in the code itself and verbally on camera when you show me the code. So I got this code from such and such in comments, and you say it when you present it. Because the idea is like you don't want to like if you wrote all this code and worked so hard on it and then someone just like shows here's this code, you don't want someone to be like, that's my code, I wrote that. So citing our sources, good practice. This includes code written by AI, so you should say this was written by AI. What was it? To what extent is it written by AI? And then compress it, give it to the videographer, or post it on GitHub. So again, if you didn't write the majority of your code, you can't put it on GitHub. You have to turn in a zip file. Is everybody clear on that? Okay. So hopefully that's not too like there's a word I'm looking for. Intensive feeling, because like you're not like you're allowed to like look at other sources. But I do encourage you to start from scratch as much as you can. The videographer is so ideally now the architect and the programmer have done their share of the work. And so the videographer is responsible for filming things, editing things, turning it in. So once the architect has done the work of here's the examples and here's how you do it, the videographer presents that. The videographer explains the code, shows the major functions, shows how the operation works, and shows the code processing the data. Once you do that, just make sure that the code is legible and not too small, and make sure to briefly explain what your coding environment looks like. And then edit it together, post to YouTube. And the videographer is responsible for turning it in. So the architect, and I've tried to kind of make it so that the roles are roughly equal. You should, as you go, try and be in communication with group members to make sure that no one's doing like the majority share of the work, because it's different aspects, and so hopefully it kind of evens out. So the idea is that if the architect comes up with all of these examples and explanations and tells it to the videographer is then able to explain it, because the prep work has been done. And similarly for the code. So now I've just got a bunch of notes. So all of your group members should know what's going on here. If the videographer is being the voice of the group, so the only one presenting, doesn't have to be. The others should be present to correct and advise while you're filming. The architect and the programmer can also choose to explain if they want. Just among your group, just choose the option that divides the work most evenly. In terms of videos, I don't care what you use to edit. Choose the option that's simplest and freest for you. There should be free editors, like I use QuickTime to just like splice things together and trim clips and stuff like that. That's fine. I bet there's a free one on Windows, or chances are there's a free one on your phone as well. So choose the simple, choose the free option. If you have extra time, you can put more work into it, but it's not required. Again, the thing that I said at the first day of class, by default, the video should be unlisted for privacy reasons. And so only if all of the group members agree can the video be made public. In terms of how I film voiceovers for the code, I'm doing that right now. So you see me on Zoom, I set up a meeting, I share my screen, and I make sure my mic's unmuted, and then I just hit record, and it records, and I talk and I scroll, and then once I'm done, I stop recording, end the meeting, and then I've got my MP4. Just keep in mind what's on your screen when you do sharing, just in general. For the animation or explanation, either maybe do it in PowerPoint and have like animations that way, or you can do like, I want to make it as easy as possible. You could like set up your computer so it's facing the whiteboard and you just like draw on the whiteboard and explain it that way. That's perfectly fine. Or there's like document cameras in the classroom. You can film with those. There's probably a way to hook up. You can probably like log in on the classroom computer and use Zoom and record that, I bet. For posting, it's preferable that you use your St. Mary's Google account to post on YouTube. That's up to you. If you've got like a YouTube account that you want to post it all to, that's fine. Keep in mind, after you graduate, you won't have access to the YouTube account. So like when I was a student, I posted a few YouTube videos. And then once I left the college, the public videos, I believe, were still available. I just couldn't log in to access that account anymore. I'm not sure about unlisted videos. Yeah. Yeah, so like we have like Gmail for our email account. There's also YouTube associated with that. So you can like create a YouTube channel for your SMC email Google account. Yeah, so the goal is have fun, make it interesting. I've given you like the bare bones, here's what you should do, what you should have. Make the toy example silly, come up with a real world example that is interesting to you. I would like it to be professionally rigorous, but fun where it can be. I think those are some of the best explanations. The goal is for you to really understand the data structure that you've been assigned to. And other than that, have fun. So these are the ideas for so I'll put you in groups. I probably won't do it today. Maybe. But these are there's 3 main ideas. There's others. If your group gets together and is like, I really don't want to do a priority queue, I would prefer to do it on a heap or an AVL tree or some other data structure. I'm open to that. But initially, I'm going to assign you one of these 3. And so since there's 30 people in this class, there's going to be 10 groups. And so we'll have multiple coverage of each of them. I'm still working on the rubric. I will let you know about that as soon as it's ready. Okay, that's the document. Thoughts? Cool. So yeah, so this is posted on Canvas now. I might end a few minutes early. And so just like think about it. On Tuesday, we will look at these data structures. I will assign groups and yeah, on Tuesday, I'll assign groups that you can meet each other and start thinking about it. And then we'll go through the data structures. Probably we'll finish them because it shouldn't take that long. And we're off to the races. Any questions before we end? Yeah. I haven't decided when this is due yet. Yeah, it'll be after homework 3 at least. And homework 3 is due March 6th.
Oh.
Yeah, so you'll have time. Make sure to give me your chapter 3. No. Chapter 2 packet. Not homework 2, the math one. Chapter 2, the analysis one. Thank you, and I'll see you on Tuesday.